In this video we are going to look at a non-homogeneous second order differential equation with constant coefficients. So that means the right hand side is not zero. It's some function of x. Now that means it could just be a constant. So let's take an example. This one here. See, the right hand side is not zero. Now a particular integral is any function which satisfies this non-homogeneous differential equation. So for this example here, we want to show that minus a quarter e to the 2x is a particular integral of this function. So that's straightforward. We just have to get the derivatives and sub in. So we differentiate this once. So we've minus a quarter times 2e to the 2x. That's minus a half e to 2x. And then we differentiate again. So using the chain rule, we get minus a half times 2e to the 2x, which is minus 1e to the 2x. So we plug these two things into the differential equation, and of course we plug minus a quarter e to the 2x in for y. So this is what we'll get. So we see that e to the 2x appears in every term. So how many of them do we have? We have minus 1 plus a half, that's minus a half, plus 6 quarters. So we end up with minus a half plus 1 and a half. That's plus 1. So we get plus 1 e to the 2x, which is the right hand side of the differential equation. So that proves that this is a particular integral. We can call that y sub p. We can call it a particular integral, or a particular solution if you like. So a particular integral is any solution of a differential equation. Notice that we don't have an arbitrary constant in it. So let's find a particular integral of this differential equation here. So we see that we have an exponential function on the right hand side. And we know that the derivative of an exponential function is that exponential function. We get it back. If we differentiate this, we get terms that have e to the 2x in them. No matter how many times we differentiate this, e to the 2x is going to appear on the left hand side. And so it's going to appear in the three terms. So we need to consider constant multiples of e to the 2x. So we just stick a constant, call it a, in front of e to the 2x. And this is our trial solution. We plug this into the differential equation. So we differentiate it once using the chain rule. We get a times 2e to the 2x, which is that. Differentiate again, we get another 2 from the power, so we get 2 times 2, 4a in front. Plug into the differential equation. So we have 4a e to the 2x, then we have a minus 2a e to the 2x, then we have minus 6 times y. So we have minus 6 times a e to the 2x. And on the right hand side we have 1e to the 2x. So you see the left hand side is just a single term involving e to the 2x. Just gather the coefficients together to get minus 4a. So the only way that both sides can be the same for all values of x is if the coefficients are the same. So minus 4a must equal 1. So a must equal minus a quarter. So here's a table of trial solutions to find the particular integral. So little f of x is the right hand side of our differential equation. So if there's a constant term on the right hand side, our trial solution should just be a constant term. We'll see some examples later. So we just go to the one we did. If the right hand side has the form of e to the power of kx, then our trial solution, as we've seen, is a constant times e to the kx. It's got the same form actually as the right hand side. Here's another example. So the right hand side has got e to the minus x in it, so we need to have a trial solution that contains e to the minus x. We just stick a constant in front of it. It's called alpha here. So we plug this into the left hand side and we'll get a single term involving e to the minus x on the left hand side. By comparing coefficients on both sides we can solve for alpha. Let's look at this differential equation here. Now the right hand side is linear in x, so you know, it might suggest that we use a term of the form constant times x as our trial solution. So we could try alpha x as our trial solution. So alpha is some constant. So we need to differentiate alpha x once. Well, that'll just give us alpha. If we differentiate it twice, well, we're differentiating a constant, so we get 0. And if we plug everything in, what do we get? Well, we get 0 minus 6 alpha plus 8 alpha x equals x on the right hand side. We have to compare both sides here. So we have an identity. This has got to be true for all values of x. So the x terms must equal, or the coefficients must equal. So 8 alpha must equal 1, so alpha must equal 1 8. But then of course the constant terms on both sides must equal as well if this identity is to hold for all x. So 6 alpha equals 0, alpha equals 0. So we get a contradiction here. Alpha can't be both 1 8 and 0 at the same time. So obviously alpha x is not a solution. But if we try a solution of the form alpha x plus beta, this will work out, I think. So let's do that. So here's our trial solution. We have to differentiate it once, well, that gives us alpha. Differentiate it twice, we get 0. And we plug into the differential equation. So we plug 0 in for this. We minus 6 alpha plus 8 times alpha x plus beta. So here's our identity. Alpha and beta are constants. So the only way this can be true for all values of x is if the constant terms on both sides are the same. So what are the constant terms on both sides? Well, we have minus 6 alpha plus beta on the left hand side, and on the right hand side we have 0. Also the x terms must be the same. The coefficient of x on the left is 8 alpha, the coefficient on the right is 1. So now we can actually solve between these equations here. Alpha is 1 8, and if we plug 1 8 into this second equation, we can find beta. So having found beta, we can write down our particular integral. Let's take this differential equation here. Now the right hand side is cos of x, and we know if we differentiate cos of x repeatedly, well, we get sine of x, then we get cos of x, then we get sine of x back, and so on. So that suggests a trial solution that involves cos of x. But it's also true that if we differentiate sine of x repeatedly, we get cos x, then sine x, then cos x. We just cycle through the same functions. So we could try this, a linear combination of cos x and sine x. So let's take the first derivative of this. The derivative of cos of x is minus sine x. The derivative of sine x is cos x. Now for the second derivative, differentiating sine x, we get cos x. If we differentiate cos x, we get minus sine x. So now we substitute these and of course y into the differential equation. So we substitute it into this here, and this is what we get. So here we have an identity. The only way that all of this is true for all values of x is if the coefficients of like functions are the same on both sides. So let's look at the coefficients of cos of x on the left hand side. Well, we have minus a for this one, we have minus 6b for this one, and we have plus 8a for this one, and that must equal 3. So minus a minus 6b plus 8a, well, that's going to be 7a minus 6b. 7a minus 6b must equal 3, and then we equate the coefficients of sine. So we have minus b minus 6a plus 8b. Well, that's 6b minus 6a must equal 0 because we have no sine term on the right hand side. So if these are true, then the identity will be true for all values of x. It doesn't matter what x is, this will be true. We have two equations and two unknowns, and we can find a and b. So that's just a straightforward solving of simultaneous equations. So once we get a and b, we can plug in. So we have a cos x plus b sin x here. Now, in the last section we found particular integrals or particular solutions of non-homogeneous differential equations. In this section we're going to get general solutions of non-homogeneous differential equations. To do that, we're going to get the complementary function for this differential equation. Now, all that is the solution of the corresponding homogeneous differential equation. So the homogeneous differential equation has 0 on the right hand side. So the left hand side is the same, of course, but the right hand side is 0. And we covered how to solve them in detail. We get the auxiliary equation. So we have 1k squared plus 3k minus 10 equals 0. And if we solve that, well, we did it in a previous example actually. factors of minus 10 are minus 5 and plus 2, and you can check that you have 2k minus 5k. Actually, it's the other way around. This should be plus and this should be minus. Well, we have them listed here anyway, but just to go through it, then we know that we have two solutions. One of them is e to the minus 5x, that's one solution of the differential equation, and the other one is e to the plus 2x. So we just solve this, you know, we get k equals minus 5 and k equals 2, and y equals e to the kx is a solution of the differential equation. So we just plug each of these values of k in turn into this. Anyway, so these are solutions of the homogeneous differential equation. So since they're linearly independent, we can get a linear combination of them. The linear combination of them is also a solution of the homogeneous differential equation, and that solution is called a complementary function. So that's the first step. We solved the corresponding homogeneous differential equation. Next, we get a particular solution or a particular integral for the equation for the non-homogeneous differential equation. This is this one here, what we're trying to solve. Now, the right hand side has the form of a quadratic in x, ax squared plus bx plus c. So our trial solution will be a function of the form ax squared plus bx plus c, same form as the right hand side. So we differentiated once to get 2ax plus b, we differentiated again to get 2a, and we plug these and of course y into our differential equation. So we plug 2a in for the first term, and then we've 3 times 2ax plus b for the second term, and then we've minus 10 times ax squared plus bx plus c for the third term, and on the right hand side we've 3x squared. Now we have an identity in x. The only way that both sides can equal each other for all x is if the coefficients of like terms are the same. So the x squared term on the left hand side is minus 10ax squared, and on the right hand side the x squared term is 3x squared, so the coefficients must be the same. So minus 10a must equal plus 3, so from that we get a equals minus 3/10. The coefficients of x must be the same on both sides. The coefficient of x on the left hand side is 6a minus 10b, so that's it here. The coefficient of x on the right hand side is 0. We have 0x on the right hand side. And finally, the constant terms on both sides must be the same. So the constant term on the left hand side is 2a plus 3b minus 10c, and the constant term on the right hand side is 0. So we have these three equations. Having found a, we plug into this one up here to find b. So a is minus 3/10, so we plug minus 3/10 in here, and we solve this one for b, and if we do that we get minus 9 over 50. Having found a and b, we plug into this top equation here to find c. So now we can write down our particular integral, our particular solution. So we plug in for a, b and c. Now it turns out that the general solution of the non-homogeneous differential equation is got by summing the complementary function, that is the solution of the homogeneous differential equation, with the particular integral. We just take the sum of them. So we take this and add it to this. So here's the point. Here's our non-homogeneous differential equation. The solution of it is the sum of the particular integral, denoted y sub p, and the complementary function ycf. Now I'll run through a proof of this. Okay, so here's our differential equation. Here are our two solutions. Let's plug each of them in turn into this. Okay, so this is the result of plugging our particular integral into the left hand side. It has to work out to the right hand side since y sub p is a solution, of course, and we do the same for the complementary function. Okay, the complementary function is plugged into the left hand side, but that gives us 0 because the complementary function ycf is the solution of the corresponding homogeneous differential equation. That's the one with 0 on the right hand side instead of f of x. Next thing we do is just add these together. So we add the left hand sides together and then we add the right hand sides. I've left out the y here. So in this second equation here we have y times p. That's the particular solution of this differential equation. So if we plug yp into the left hand side, we have to get the right hand side. Now ycf is a solution of the corresponding homogeneous differential equation. We get 0 on the right hand side. So we just add these terms together, add these, and then if we add these together and factorize out to c, we have to get the right hand side, the sum of the right hand sides, f of x plus 0. Well, that's just f of x. Notice here we're taking the second derivative of y sub p and the second derivative of ycf, but we can write that as a times the second derivative with respect to x of y of p plus y of cf. And we can do something similar here, of course. We're just using the fact that the derivative of a sum of functions is the sum of the derivatives. That's a well-known fact. We use that all the time when we differentiate. And that's the end of our proof. You can see now that we've shown that this thing here, the sum of these two, is a solution of the differential equation. So yp plus ycf is a solution of this differential equation. It hinges on the fact that when we added the two equations together, we were adding f of x with 0.